Hi, I'm Thomas Eimann and I'm introducing the paper Hand Pose-Based Task Learning from Visual Observations with Semantic Skill Extraction, authored by Seishu Kiyo, Thomas Eimann, Gilles Li, and Donghee Li from the Technical University of Munich. We present a framework for the learning from demonstration on the task level, where we estimate the human hand pose to directly learn a task and segment these tasks into skills in order to optimize and adapt the skills in the execution according to the environment. The motivation is that end users want to intuitively create tasks by hand demonstration, so we need to solve the correspondence problem between human hand and the robot. Also, end users want to understand what the system has learned, so we need to segment the task and extract meaningful skills to present it to the user. Also, end users provide non-optimal demonstrations, so we optimally execute these skills to outperform the demonstration. The related work shows that in the learning from demonstration domain, kinesthetic teaching is the common way to learn a task and segment it into skills. In the teleoperation and imitation learning domain, visual hand observations has been used to learn a task from the human or to directly teleoperate a robot from the human hand. Further, the robot skill formalization has been introduced by Patterson et al., which introduces a task, a skill, and a device primitive layer. Then, a skill segmentation from human motion has been shown by Lin et al., where zero velocity crossings has been used to segment the task, and these segments have been encoded by hidden Markov models to be compared with future observation sequences. Now, we explain how we capture the demonstration from the human. We use an Asus XGM Pro to record the human hand pose. Then we estimate the joint positions. We extract a coordinate system from these joint positions and map these to a robot's two-finger gripper. We learn skills templates from prior demonstrations to be encoded in a hidden Markov model that we use as a probabilistic classifier. Then we are able to assess the similarity between an observed sequence and the learned model by using the forward algorithm. On the left you see an example for a specific computed feature, which is the distance between the fingers, and then the learned model can be compared with future observation sequences. We proposed a set of skills you see on the left and a set of features you see on the right, which is based on velocity and distance features between objects and the demonstrator's hand.
Now we come to the segmentation part. The segmentation process can be divided into two stages: the segment point modeling stage and the template matching stage, which in turn consists 3 units: probabilistic classification, skill labeling, and skill semantic ordering. In the first stage, segment point modeling, the main idea is to determine possible segmentation points to divide the data into data sections. We use several features to determine an initial over-segmentation. A segmentation point is placed at location where the predefined threshold on each feature has been crossed. In the second stage, we perform template matching on the over-segmented data sections to reduce the number of data sections and label them with skills. In the probabilistic classification unit, we use the previously learned HMMs to calculate the likelihood of an observation sequence related to each possible segment. The idea of skill semantic ordering unit is that we assume there is a logical order of skill execution. You can use this information to evaluate the segmentation success or to reduce the computation by leave out some skills. In the skill labeling process, we use the TCP profile as a heuristic to differentiate between action skills and move skills. Move skills are considered to be connector to connect the action skills. We then use all the features to find the final skill. Now we come to the result part. We differentiate between simple replay and execution with skill knowledge and DMP. In the left, we can see the human demonstrator performing some pick and place tasks with markers attached on the table and the objects. In the right, we can see the result of the task in the robot simulator, Copalia Sim. We first try to replay the demonstration. The red block represents an object whose position has been changed during demonstration, and the robot uses dynamic movement primitives to still be able to perform the same set of actions. We have tested our system with multiple experiments of different set of skill combinations. In the left, we can see the segmentation results of an exemplary experiment. We compare our segmentation method with 3 different segmentation methods. The ground truth is where a human observer manually annotates the skills. In a proximity area-based method, we have the states within proximity area and out of proximity area state. In the gripper distance-based method, we have the gripper closed and gripper opened state. We can see that our method produces similar results with the ground truth, with only some minor inaccuracies in the position of the segmentation points. The other 2 methods are simple to implement, but are not able to find all the skills. We optimize our execution with predefined skill knowledge. As mentioned before, we consider the move actions as a connector, and thus we replace with linear motions and achieve an overall path length reduction of 7.5%. We do not map the human fingertip distance to the gripper, but instead we obtain locations, send discrete gripper control commands through the recognized skills. We integrate dynamic movement primitives to make our learned execution more adaptive to the environment, in particular if the position of the object has changed. To summarize, we have created a system which approaches towards tasks definition for end users without expert knowledge. A system which allows intuitive task creation relying solely on a vision system and automatically segments the tasks and recognizes skills, which is a foundation for further execution optimization. In the future, we want to further increase the robustness in the handpost estimation, generalize our skill templates to more complex scenarios, and find a possibility to optimize the found segmentation. Here are the references. Thank you very much for your attention.